So now that we've talked about the idea of a bond energy and how that's how much energy it takes to break the bonds in a molecule, we can look at bond energies as a way to approximate enthalpies of reaction. If we remember, the enthalpy of a reaction is a way of looking at how much energy is either absorbed or released when a chemical reaction happens. And if we're thinking about this in terms of bonds, that's going to be, we're going to have to put in energy to break all the bonds in the reactants. And then to form the products, they're going to form bonds, and that releases energy. And so the net, once you put in the energy and then gotten energy out from making new bonds, is what we know as the enthalpy of reaction. And so using these average bond energies that I showed in the table in the previous slide, we can get an approximate value for enthalpies of reaction, like how much energy net do we either get out of the reaction or have to put into the reaction to get it to happen. So we'll look at this with the example of this reaction of the combustion of methane. We've seen this reaction a few times. Methane plus oxygen gas, I'm leaving off the states here, forms carbon dioxide and water. And to get this balanced, we need 2 moles of oxygen and 2 moles of water. All right, so I think we've done this. We've looked at this reaction in several different ways in different contexts. So what we can imagine is this picture that we have here. We can imagine starting with, let's use this color. So we can imagine starting with our methane right here, so that's CH4, and our 2 oxygen molecules, right? And so these methane is bonded with 4 single bonds between the carbon and hydrogen. And we can break those 4 bonds in this here. So that's why we have a 4 here, and this value of 413 kilojoules, this comes from our table over here. So a CH bond has a bond energy of about 413 kilojoules for a single bond, and then in our oxygen we have an oxygen-oxygen double bond, which is right here, and it has a bond energy of about 498 kilojoules per mole. So again, these are average values, and this is only approximate because the actual values specifically for methane and O2 are going to be a little bit different than what is in that table because that's averaged over a bunch of different molecules. But for our purposes, we can use those values from the table. Let me get back to my blue pen here. So where we have our 413 kilojoules, we have 4 bonds that are breaking, so we multiply that by 4, and our 2 bonds, 2 oxygen-oxygen double bonds, and our 2 different molecules of oxygen that are breaking. So we're imagining in a whole mole of methane and 2 whole moles of O2, we break all the bonds. When we add those together, so we get this number here. So this is 4 plus, not 4 plus, but 4 times 413 kilojoules per mole, or kilojoules, plus 2 times 498 kilojoules. So that's where this number is coming from. And this is the energy. Now, this is not how the reaction actually happens, but it gives us a way, again, a reference point. We're comparing it to, we break all the bonds, and then we put all the bonds back together in a different arrangement to make our products. So when we're thinking about making our products, we get the opposite effect that happens. When the bonds form, that releases energy in the form of heat often, or it can be other ways. And so we're going to form 1 molecule of carbon dioxide, and so that forms 2 carbon-oxygen double bonds. So there's 1 right here and 1 right here. And so that's going to be, let me give myself, but right here, this 2 times negative 799. Now it becomes negative because when we form bonds, energy comes out, right? So it releases energy. So that's where the energy is coming from. That's why it's negative. It's exothermic, right, this process. And we also have 4 oxygen-hydrogen single bonds, right? So we have 2 per water molecule that are forming here. And so when we add those numbers together, we get negative 3,450 kilojoules. So our net, once we add these together, is we have our amount of energy, so energy in was 2648 kilojoules. Our energy out was negative 3450 kilojoules. And when we add those together, we'll get our net energy, or basically this is our enthalpy of reaction, approximately, right? This is not exact. If you want the exact value, you would need to do a calorimetry experiment. But when we add those together, we get a net of negative 802 kilojoules. And that's an approximate value for the enthalpy of reaction for this reaction. All right. So we can do this with other reactions as well. We'll get some practice with this in class, but this is the basic premise of this idea. So we can write this up in an equation, just so you have that as well, that the enthalpy of reaction, again, approximated using these bond energies, is that we're going to take the sum of all of the enthalpies, or the bond energies for bonds breaking, minus the sum of the enthalpy for all the bonds forming. So again, that's why we have this negative sign in this value up here, which you can't see, now it's behind my head. Right, but this negative 3450, it has this negative sign. That same negative sign is reflected right here, because when the bonds are forming, that's releasing energy. All right, and so that's the basic idea behind how we can approximate values for enthalpies of reaction from these bond energies. So we just got a couple of miscellaneous things to go over in the next couple of videos, and then we'll be done with chapter 8. One is talking about, again, this was already covered in class, I just want to make a video so that you have it for studying purposes, about ionic bonds and their strengths. And then the final thing is a little bit of an introduction to the way we draw organic molecules, so molecules involving carbon, hydrogen, oxygen, nitrogen, and how it relates to the Lewis structures we've been learning, so that you can interpret some of these structures you probably have seen of chemicals, and just getting you an introduction to that, so that you know a little bit more about that.